Okay, take 430, integration of parts. Now, in your notes, you'll notice that I have I late written down. Now, what this is for is when we go to integration of parts, we're going to put one part for what we call U and another part for what we call DV. And what this rule here is it helps you know which one goes where, and that's this. Whatever comes first out of these letters goes for the U. The other part goes for the DV. Whatever's first. In other words, if you had the log of something and then times the trig function, then the log part would be the U part and the trig part would be the DV part. And I'll show examples of that. But kind of remember that it helps you know which one to let be U and which one to be DV. Okay, let's look at the first example. First example is the integration of x squared times the log of x dx. Okay, now when we have this, we're going to let one part be u, another part be dv. Now the u part we will take the derivative of, and the v part we'll integrate. Well, I gave you the rule I late to know which one comes first, but also reason. You don't let the log of x be the dv part because you don't know the integration of dv. So you kind of have to put some part in here that you know you can integrate for the dv part. Now the du part you're going to take the derivative of. So it could be the one here. Alright, so now let's look. We have x squared log of x. So now looking at our u dv. So over to the side on your paper, you should write down u equals dv equals. All right, remember now log comes before algebra. L comes before A. So therefore, log goes for the u, and the x squared dx goes for the dv. You now take the derivative of the u part, and that will be du. Derivative of this is 1 over x dx. And the integration of this, if you integrate this and integrate this, then that becomes v, and this becomes x cubed over 3. So there's the decision of what you let be u and what you let be dv. U you take the derivative of, v you integrate. And now you go back and plug it in. So now plugging in, remember now, the rule is u times v, okay, so this is u times v minus the integration of v du. V du. Well, v was this, and du was this. All right? So that's integration of parts. V, the integration part, the original part before you took the derivative, minus the integration of, after you integrate, times after you take the derivative. And then from there, you finish the problem out. So this x will divide out with this, and leave this x squared. So we now have x cubed over 3, log of x, minus the integration of x squared over 3 dx. The integration of this is x cubed over 3 times this 3, and so we have the answer. Very simple integration from that step on. Okay, let's look now at the next example. The next example is the integration of x times e to the x dx. All right, so we have to decide that one part. Well, this is algebra, and this is exponent. That's A, that's E, so this comes first. So let's go over and look at our u dv bit. So for u, we let this be the x part, and its derivative now is 1. And we let this dv be the e to the x dx, and the integration of e to the x is itself. And so we have now u times v minus, and this is what I like to show. It's this times this, minus the integration of this times this times this. UV minus the integration of V du. So this times this minus the integration of this times this. So let's go look at the problem here and see what we have. We now have U, which is x, V, which is Ex, minus the integration of V du. Now, finish that out. Integration of V dx is itself, and so, again, very easy problem once we set that. All right, let's look at example 3. Example 3 is x times inverse tangent of x times dx. So what we have here is inverse, that's the I, so it's going to come first, it's going to be the U part, and then x and dx will be the dv part. So let's come over and look at that then. So U is going to be I, inverse tangent, and dv is going to be x dx. The derivative inverse tangent is 1 over the object squared plus 1 times the derivative of the object, which is 1. And the integration of this is x squared over 2. So what we have is uv, this times this, minus the integration of this times that. So let's go back and look at the problem again. So what we have is u times v. U is inverse tangent, v is x squared over 2. Minus the x squared over 2, put the 2 out in front, x squared over 2, times the 1 over x squared plus 1 dx. Now, how do we integrate this? Anytime the power here is equal to or greater than this power of polynomials, we do long division. When you do long division, divide this into x squared, you get 1 minus 1 over x squared plus 1. All right, finishing this up, integration of 1 is x. Integration of this is inverse tangent. And moving the brackets, we get 1 half x minus times a minus 1 half inverse tangent plus c, and we have the problem worked. All right, next example. And the next example is one where we have to do integration of parts twice. And so I want to show you how this one works. All right, what we have is the integration of x squared cosine. Well, that's trig, and that's algebra. So it means that, let's go over and replace this u and dv part. So algebra is first, trig is next. The derivative of this is 2x. Integration of this is positive sine of x. All right. So now let's go substitute in the problem. So we place u, v, minus, I move the 2 out. It was 2x, but I move the 2 out here. Minus 2x dx times the sine. Well, what happens now in this type of problem is you have integration parts again. We have to do it one more time. So let's look at this now. This is algebra and trig again. So we'll go over, and x will be the u, and v, dv will be the sine, and the integration of that is a minus cosine. The derivative of this is 1. So what we have then is x times a minus cosine minus the integration of this times that. So let's go look at the problem and see about that. Well, sure enough. Now, listen. Here's what I want you to see. If you have a constant in here, move it out in front and put brackets here and keep that number away from this part here until you get this finished. That's the safest way to do it. Okay. So clear this out of any constant that you can. Keep it out in front. Keep it in front of the brackets. Okay. And then when you get this all worked out and you integrate this, then bring that constant back in the problem. So integration of this then was that x times the minus cosine of x. Okay. And then minus the integration of 1 times the minus cosine. All right, well, removing brackets, now look what happens. This minus times this minus gives us a plus. Now pay attention to this. We have a minus 2 times a minus times a minus, which would then be a minus 2 times, and the integration of cosine is a positive sign, plus c. Okay, let's look at some more examples. Okay, this is the problem where we have to do this twice and move something across. So this is a very important one to pay attention to. It's going to be kind of, camera moved back, hard to see maybe, but hopefully you can follow the notes. But follow where I'm pointing at what I'm doing. All right. So we have E and trig. E and trig. So T is first, and then E is second. Therefore, U will be the sine of 3x, and dB will be the E of 2x. So the derivative is, derivative sine is cosine, derivative of the angle is 3. The integration of e to 2x is itself provided we have the derivative of the power. So the derivative, this is 2, so we have to put a 2 here and 1/2 out in front, and so that's where the 1/2 comes from. The integration of e is itself provided we have the derivative of the power here. So the derivative of the power, we have to place a 2 and 1/2 out in front. So the integration of that is that. Therefore, now, I want you to look at the whole problem stretched out. And I want you to see this. When you have to do this twice, then you better learn to keep things in order. Write this down again, equals, and then use your UV, dVu. Right? So we're going to write the original problem, equals. Then we're going to come along and say U times V, so that's 1/2 E sine, minus this 1/2 times this 3, put it out in front, and then e to the 2x times the cosine of 3x dx. We have to do this again. Okay. So we go do this again. We're doing this again. We go do the trig up here, so this will be cosine, and the derivative of that is minus sine, and we're going to integrate this again, so it'll be that again. So this is where I said earlier in the tape, be very careful about your algebra. So what we have is this 3/2 right here times bracket, and now this times that is equal to 1/2 e to the 2x cosine of 3x plus 3/2 because of the minus times the minus 3/2 integration of this. Now, looks like we have to do it again. No. When we come back to this step, we have come back to the original problem. So what we do now is remove the bracket. So we have a minus 3/4 times this, and a minus 9/4 times this. We now take this across, just like if I had x plus 3 minus 2x. I would move this across and make it 3x's is equal to 3, and then go solve. So that's what we're going to do. Watch this. We're going to take this and move it across. So we're going to leave these two there and move that across and add it to one of those. Now just all of a sudden I came up with 13/4. If you look in your notes, what I'm saying is this 9/4 over here added to one of those makes 13/4. Now let's go back and look at this for a moment. When we were solving for x, we divided with the number for the x. So let's go back over here, and we're now going to divide everything by flipping this over and dividing it over here, or multiplying by 4/13. So we're going to invert and multiply 4 over 13 times 1/2 is 2 over 13. And 4 over 13 times 3/4 is 3 over 13. Plus C, that's how you do that. I want you to notice a trick on something like this. E times sine or cosine ends up being whatever the number in front of the x is here, whatever the number of the E part, whatever the number in front of the x is for the trig is here, and this squared, 3 squared plus 2 squared is equal to that. Little trick there you might pick up. All right, so here's one where looking at the whole problem. Here's one where you will do integration of parts twice, and you'll come back and end up having the same thing you had to start with, but a different number here. You better not get a plus 1 right in here, or this would divide out and not go across and add. Okay, that's a long, tough one, so now let's look at a couple of easy ones. The next two examples, this example, is the idea of you don't have parts, you just have one single object there. So what do you do if you have the integration of something here, it's just a single thing, and doesn't look like parts, but yet it can be made to be parts because of this. We will then let u be the log of x, and dv be just a 1 dx. So we really still have parts. We have the log of x and we have the dx. Taking the derivative, integration, and look how simple it is. It's this times this minus this times that. So looking at the problem, we have x, log of x minus integration of 1 dx. Integration of 1 is 1x. So it's a very simple idea. But I want you to be aware of using integration of parts when you really kind of have just a simple single object there. Next example is inverse tangent. So we simply let inverse tangent be the u part, and this will be a 1. So therefore, the integration of 1 is x. So we're going to have x times that. So there it is. There's ub. And then we're going to have x times the derivative of this. And so we have this. Well, there we have that. What's the integration of this? Is if I go put a 2 here and 1/2 out in front, the answer is log of the denominator. If I have a denominator and everything around it is derivative, then it's the log of the denominator. So we have that problem. All right, now let's look at the next example, integration of secant cube. Now this is one, here's how it works, but after we get through, it would be advisable to have this memorized. You'll encounter this quite a few times in other parts of integration. The integration of secant cube. The integration of secant cube. Now here's one where we just kind of do the Pierce rule again. We make it work out. We're just going to split it up, and we're going to let u be the secant of x, and we're going to take 2 of them and let dv be secant squared. The reason is because I know the integration. So we're just going to split it where we know integration of one part, and we know the derivative of the other part. And so that's how this works. So the derivative of secant is secant tangent. The integration of secant squared is tangent. So therefore, it's uv minus the integration of this. So the integration of secant cubed is secant tangent minus the integration of secant tangent squared. Well, this one can't be integrated straight off like this, but we can by using techniques of integration, trig substitutions. So the tangent squared is equal to secant squared minus 1. And then removing parentheses, we have the integration of secant times, oh, that's secant cubed. We can move that across. That's like we had to start with. So we'll move it over to the other side and add it to that other secant cube. And then over here we have a minus times this minus secant. And we know the integration is secant, so we've got it made. So looking, kind of backing out, looking at this, I'm moving this across and making two of those, and I'm writing this down here. So what we have is two of those equals secant tangent plus integration of secant. And now we go do what? With that 2, we come over and invert and multiply. So we have 1/2 secant tangent, and we have 1/2 of the integration of secant, which is by memory the log of secant plus tangent. Absolute values, don't forget that, plus c. All right, the next example, I'm not going to put on the board here on the screen, but you can look at it. It's just another example. Here's one that usually you're taught to do by trig substitution, but it so happens it can be done by integration of parts. Again, kind of splitting up to make it work. So you're going to put an x squared for the u, and you're going to put an x over the square root, and then that can be integrated by the power rule. So by the power rule. And then you do the power rule again. Just to let you know that some problems can be done in 2 or more methods. All right, this concludes the tape. I should give you enough examples here to be able to handle most of the problems you'll ever run across in textbooks to deal with integration of parts.